new notation. So if you write the word id, and then you write down any term as a subscript for that, then the result will be overall a term. So if you take some object and then you put it as subscript for id, then this symbol refers to some object, which we are about to define. So this is going to be what we call the identity function on a set. So if I say id subscript x, then this is called the identity function on x. And what it's supposed to mean is it's supposed to be a function that does nothing. So I think of it as the do nothing function. Input something and then nothing will happen to it. So if you think about it in terms of, let's pretend that capital X is this set consisting of 4 things. If you think about it in terms of these diagrams we've been drawing to depict functions or any sets of pairs, then the idea for the identity function on x, id sub x, is that it's supposed to have this picture where it's going from x to itself, and it's just sending everything along to itself. So A goes to A, B goes to B, C goes to C, D goes to D. It does nothing, right? As opposed to, say, a function that swaps A and B and maybe sends A to B and B to A or something. No, this one does nothing. So formalism, when I say id subscript x, that's the set of little x comma little x such that little x is an x. That's the definition. And really this is a shorthand, right? Because I'm not putting a variable here, I'm putting a complicated term. So actually what I'm defining is the set of, let's call them p's, I like to use p for pair, such that there exists some x such that p is this and x is in big X. So this is it, fully expanded out. So, to start with, id sub x is just defined to be a certain set of pairs, right? But you can also, from here you can prove that it's a function. And if you do, if you're okay with those kinds of conclusions, then you can define it using a formula. So you can say id sub x is defined by saying that its value at x, so this is a capital X subscript and this curly x is the elements of x. So this is the definition in terms of a formula. Its value at x is x for all x in there. But I'm going to define it like this, and then these will be things that we can prove. And then for LaTeX, if you just want to write this, I would say use, for the word id, use operator name or text would be fine, like this. And then for the subscript, you just do an underscore. So if it's just one thing, like id sub x, then underscore x would work. But if it's, something longer, like A union B or something, then you need to group it in curly braces. So A union B would be A cup B, like this. And this is all assuming you're in math mode, so this is the stuff that goes between the dollar signs. All right, so common LaTeX mistake is to forget these curly braces, and then you'll just get id subscript A, and then the union B will be big rather than being a subscript. So use the curly braces to group things. So what we're looking at here is definition sorry, I looked it up and instantly forgot it. It was definition 64 is this. And moving on from here, let's prove some basic facts about the identity. So we just got done defining the identity function on a set like capital A as this. So let's look at Theorem 65. So first of all, the identity function on capital A is a function mapping capital A to capital A. So remember, this contains 3 statements. This is saying that it is a function, and its domain is capital A, and its range is a subset of capital A. Secondly is the formula that I wrote down. So this is something that you can prove using kind of the essence of evaluation, so that you can relate these kinds of statements, a pair being in a function, to these kinds of statements about evaluation. So this is pretty quick to prove using essence of evaluation. So this is what I mean by do nothing function. It does nothing, right? You input x and it just outputs x right back with no changes made to it. And parts 3 and 4 justify calling the identity function the identity function. So why the symbol id? Why call it identity? So where else have you heard the word identity? It often comes up in algebra. Like there's these terms, or let me introduce it this way. For arithmetic, when you're adding numbers, if you think about the way addition works, there is a special number, 0, which when added to numbers leaves them unchanged, right? And it happens in both directions. This property of 0 leads us to call 0 the identity for the operation of addition. So the identity for plus is 0. So identity is that which, when operated with other things, leaves them unchanged. Similarly, there's an identity for multiplication. So there's something that when you multiply leaves things unchanged, namely 1. So you would say 1 is the identity for multiplication in arithmetic. So here, this new function that we're defining, the identity function on a set, is an identity for not addition, not multiplication, but for composition. And that's what parts 3 and 4 are saying. If you just focus on the conclusion here, it's saying when you compose, it leaves the thing unchanged. F composed with this identity, it's like multiplying by 1. You just get f back. Or it's like adding 0. You just get f back. And it happens in both directions. But composition, as we saw in the previous lecture, composition is only a very friendly operation to work with when you've got things matching up. This was back in essence of composition. When you've got the codomain of one function matching up with the domain of another. So in order to get these to work properly, we're going to need some assumptions about mappings here. Okay, so I'm just going to prove 3 in this lecture. And 1 and 2 are very easy. I'm going to prove 3, and you can see 4 in the notes. Okay, so here's my statement of part 3 of Theorem 65. So part 3 here. Except I have not written it fully out yet. So it's, if f maps A to B, then f composed with the identity function equals f. Except there's no such thing as just the identity function. There's the identity function on a set, right? I need to put a subscript here to decide what kind of identity function I'm looking at. And the statement of the original theorem tells me what to do, but I want to show you how to think through it. So there's no such thing as id. Now what goes here then? What fills this question mark? So to make this composition be friendly, what needs to go there? Well, I've got sort of, I like switching over to this kind of notation where I write the name of the mapping or the name of the function on the arrow as a decoration on the arrow rather than to the left of it like that. So f maps A to B, right? F sort of takes elements of A to elements of B. Then what is this composition? When I do f composed with something, it's like this, right? Because the notation is kind of backwards. This composition is like do this thing first and then do f. Then what kind of identity function do I want in order for the composition to make sense? It has to be an identity function whose codomain is A, right? So then A. All right, and I'm going to allow myself to use the previous parts here. While proving part 3, we can use parts 1 and 2. We're assuming they're already proven. So the identity function on A maps A to A. Similarly, the identity function on B maps B to B. And this is why in part 4, it's still using A. Oh, that's because I switched around the letters. Okay, that's a little bit confusing. But yeah, let me frame it this way. If I wanted to talk about F composed in the other direction with the identity of something and have that equal F, then the something here would be B in order for that to work. So there I'd be looking at F goes from A to B, and then what kind of identity is needed here? The identity B to B, the identity function on B. Okay, so that is a way to remember what kind of identity function to use when you're writing these things down. So let's prove this theorem. Proof. And let's assume the hypothesis. Assume F maps A to B. Then our goal is to prove that this set equals this set, right? And if we just view it that way, that these are sets, I mean they are sets, they're sets of pairs, and if we view them that way and just say, well, we're trying to prove these two sets are equal, then what strategy do you think we'll take? Probably we'll split the theorem into two parts, one to prove one inclusion and one to prove the other inclusion, along the lines of our Theorem 10. However, there's a better way. You can do it this way, but it's kind of awkward. It's often more natural to use evaluation when you're talking about functions, like to write things like f of x and things like that, rather than focus on pairs being members of f, like that. So there is a way to prove this equality rather than using inclusions by focusing on evaluation. And that is something that was one of your possible presentation problems. And whether you present or not on this one, you should definitely be aware of what it says and that it's available for you to use. So this is about equality of functions specifically. So it sort of replaces Theorem 10 when the things you're looking at are functions specifically. So if you have two functions, f and g, then they're equal if and only if the domains match up and the outputs match up for any given input in the common domain. So that's what we're going to use. So in order to reach our goal, we must prove that, so let's see, we're using Theorem 53, so by Theorem 53 we must prove that the domains of our functions match up and that the outputs match for any given input in the common domain. So we must prove that the domain of f composed with id A matches up with the domain of f. This is the equality I'm trying to prove. And that f composed with id A of x equals f of x for all x in the common domain, whatever that is. Okay, but f maps A to B, right? Since f maps A to B, the domain of f is A. And I'm allowing myself to use previous parts of this theorem here. So I'm assuming I've already proven this not very hard to prove fact that the domain of id A is A. So by Theorem 65, which is the one I'm on, but a previous part, part 1, the domain of id A is A. But that doesn't quite help, at least not directly. Yeah? I'm trying to say something about not the domain of id A, but the domain of f composed with id A. So Here's where that essence of composition theorem is helpful. Basically, anytime you're doing a composition, you're probably going to use that. I mean, most of the time when you do compositions, the things involved will be functions, and you're just going to be using this theorem pretty much every time. So if you can use part 2, that certainly makes things easier, since part 2 sort of contains part 1, but also gives you more information all in one neat package. So let's see. If I've got a function mapping one set to another set, and then another function mapping that codomain to yet another set, then the composite is a mapping of this type. So by theorem 63.2, let's see what conclusion we can draw. By theorem 63.2, the essence of composition since F maps A to B, or maybe it's more natural to talk about this one first. Since id A maps A to A, this is by the theorem that I'm on, a previous part 1, and F maps A to B, we have that this composite maps, okay, then you follow along the arrows. So this is like x to y, y to z becomes x to z. Here, A to A followed by A to B. So it becomes A to B. So that's what the essence of composition got us, is this nice package here. So in particular, it's telling us about the domain of F composed with id A, that it's equal to the domain of F, right? It's equal to A, first of all, and we already pointed out that that's the domain of F. So we have done one of the two things that we need to do. We've proven that the domains of these two functions match up. Then next we need to prove that the outputs are equal for any given input. Yeah, I just wanted to point out, by the way, we could have used this directly to argue that the domains match up, and that's fine, but if you can use this one, I always find it more intuitive. It's easier to follow along these mapping arrows than it is to think about this. Remember, this used this in the proof. So this package contains a lot of the previous stuff. Okay, so now my goal is to prove this second green underline thing here, that this at x equals that at x for all x in the domain of F. Okay, so this is a for all x kind of statement, right? So I need to use universal generalization. So now consider any x in the domain of F. And let me help the reader out a little bit here and say what I'm going to do. We will prove that F composed with id A and F take the same value when evaluated at x. Now, how do I do anything with F composed with id A evaluated at x? So here's a bad plan. Here's a bad idea that would be too much work, but it's not really a bad idea. I think it's what you would naturally think of first. I want to prove something about a composition evaluated somewhere, so I should use probably the definition of composition along with the essence of evaluation. Probably those things will get involved. And that's a very reasonable thought, but we have already done that work. The only reason it's a bad idea is that we already did that work, so we should use our previous results. We have done that work in proving part 1 of essence of composition. I think earlier I said part 2 includes part 1. That's actually not true. I don't know why I said that. They both say interesting things. Yeah, I know why I said that. Part 2 includes the aspect of part 1 where we're saying that the composite of functions is a function. That's included in part 2. But this, what happens when you evaluate, is not included in the statement of part 2. So here's a way to talk about evaluating a composite somewhere. The work is already done of using the definition of composition. So by Theorem 63.1, a composite evaluated somewhere is this iterated evaluation, one evaluation and the next. So 63.1. By Theorem 63.1, this is f of id A of x. So, well, hang on. So what's id A of x? Go to our facts about id A theorem, the one that we're proving right now. Part 2, also a previous part. Id A does nothing. So, by Theorem 63 part 2, 65 part 2, sorry. By Theorem 65 part 2, the previous part of the theorem that we're working on right now, this is this. So let me repeat this statement up here, but replacing id A of x by something that it's equal to, which is x. And that's it. We've proven what we set out to prove. We said we would prove this, and we did. Maybe I shouldn't put the box yet, since I haven't pointed out to the reader why. Oh no, I did point out we must prove these two things, and we have proven these two things. But I should give some indication here that I'm using this equality of functions theorem, Theorem 53, in order to know that proving those two things is sufficient to get the equality of functions. So let me just add that at the beginning here. Using Theorem 53, it is sufficient to prove that these two things hold. It is sufficient to prove these. Okay, and then we did prove them, and so we are done. So there's the identity function. It's an identity not for addition like 0 is, or for multiplication like 1 is. It's an identity for composition. And when you think identity function, I hope you always ask yourself, identity function on what? There's no such thing as just id. But when you think identity function on x, on some set x, think of this picture of all the points in x just getting mapped to themselves. The function does nothing. It sends any given input to itself. And there's a nice interpretation of this idea of it being an identity for composition, for the operation of composition, is when you're composing functions, like if I do f composed with g, then what I'm saying is I'm talking about the function that says do g, then do f, right? F composed with g is the function that does g followed by f. It's that composite. If I say do nothing, then do f, that's the same as do f.